All right, hi everybody. Sorry about the debacle with the Wi-Fi today at school. So I'm just gonna go ahead and re-record this whole lecture. Pause, fast forward, do whatever you need to do. But today we talked about how concentration changes over time. So yesterday we determined rate laws and reaction orders by looking at multiple different experiments with different initial concentrations. And we investigated how those changes in initial concentration affected the initial reaction rate. In other words, we looked to see if, doubling the initial concentration doubled the rate. Did it have no effect on the rate? Did it quadruple the rate? We were, looking at multiple different experiments in order to determine just how much of an effect the concentration had on the reaction rate, right? That's what we were trying to quantify. And from that, we could determine if the reaction was zero order, first order, or second order. We could determine this reaction order and write the rate law. But I told you yesterday that that's only one method of determining the rate law and the reaction order. There's another method that we're going to look at today, or we did look at in class today. And now you guys are going to have to do these notes at home. Okay, so what we're going to do now is we're going to look at this other method where we just run one experiment and we watch how the concentration changes over time, how the concentration of that reactant changes over time. So we don't do multiple different experiments. We don't change the concentrations of the reactants. We just do one experiment setup and we let it run. And we watch and see what happens to the concentration over time. And you're like, well, how would that tell me the rate law? Well, if you recall, when we were talking about the different orders of reactions yesterday, we said that if you had a zero order reaction, and a zero order reaction would be one where the concentration does not affect the rate at all, right? Like our rate law for a zero order reaction would be rate is equal to Ka raised to the 0 power, or simply rate is equal to the rate constant. The rate is constant for a zero order reaction. So if that's the case for a zero order reaction, if the rate is constant and does not change, if I were to graph the concentration versus time, I would see a linear relationship. Like I wouldn't get that curve that we get for first order and for second order reactions. And in fact, the slope of this line would be equal to the negative rate constant. Because if we look at this rate law right here, where the rate is a constant, like the rate actually equals the rate constant, rate is a change in concentration over a change in time. So like if I were to take the slope of this line, rise over run, that would be a change in concentration, my rise, over my change in time, my run. So my slope is actually equal to whatever that rate of reaction is. And I put a negative sign out in front here because this is a negative slope. So we would have a positive value then for our rate constant. Okay, now if I were to graph this for a first order or a second order reaction, I would not get a straight line. Like we talked about, where do I want to put this? I don't want to put it over there. Let's just put it over here. If I were to graph this for most reactions, concentration versus time, we get a curve, right? So for first order and second order reactions, these slow down over time. They are affected by, the rate of the reaction is affected by the concentration. Versus zero order, where the concentration has no effect. E has no effect. on the rate. Rate is constant. Here, the rate is not constant. This graph would be a curve and it would slow down over time. Okay, so let's go back to our example problem here and talk about how we can use this type of analysis to determine, is it zero order, or is it first order, or is it second order? So what I have here is a sample problem. And we can see it's the decomposition of nitrogen dioxide into nitrogen monoxide and oxygen gas. And you can see I'm watching this reaction take place over the course of 300 seconds. And the concentration of the NO2 is going down over time, which makes sense, right? Because it's a reactant. And so as this reaction proceeds, this concentration is going to decrease over time. So what we're going to do is we're going to take this data and we're going to graph it. Again, you could graph it in a graphing calculator, you could graph it in a spreadsheet program. I'd like you guys to know how to do this in a spreadsheet program because you're going to need to be able to share and print these graphs. Okay, so let's open up Google Sheets and let's put that data. Why didn't I preload the data? Come on, silly me. Okay. I should have preloaded the data. Sorry, you guys. Fast forward. 0, 50, 100, 200. Hey, you go do this. You go do this on your spreadsheet program too while you're watching this, right? So that you know what you're doing. It takes a little bit of practice. All right. So the next thing we're going to do is put in what those concentrations are. What did I say? 0.01. Oops. 0.01. 0.0078. 7. 0.00649. Okay. So now that I have my data set in here, I want to create a graph of this data because what we want to do is we want to look at that graph and we want to see if it's linear. Because if this graph is linear, we know that it's zero order, right? That's what we were just talking about. So I'm going to take this information, I'm going to highlight it, and I'm going to insert a chart. And I want a scatter plot. Why is this so slow? Are you kidding me? There we go. Jeez Louise. Okay, so there's my scatter plot. I can see here that this is not linear. This is clearly a curve, okay? But I do want to teach you guys something because they won't all be quite so obvious here. So we're going to go over to Customize, and I'm going to add a trend line to my graph. So underneath Series, we go to Trend Line. Click on Trend Line. We can clearly see there that that's not very linear. And the next thing we're going to do is for the label, we're going to tell Sheets to use the equation. And so here you can see the equation of my line is popping up. And I also want to show the R squared value. See this R squared value now here? 0.927. Okay. This R squared value is a statistical analysis tool that, the computer does a linear regression and reports out how close is this relationship to 1. So the closer your R squared value is to 1, the more linear the relationship or the line. So 0.927, you might think, oh, 0.9, like that's pretty close to 1. It's not, okay? Like this is clearly a curve, and this is not very close to 1, like 0.99 or 0.98. Those are a lot closer values to 1. Respectively, for these types of problems. Okay, so we've made this graph of concentration versus time. We've added a trend line, we've got the equation for the line, and we have an R squared value. And it is not linear, okay? So this is not a zero order reaction here. And what I'm gonna do is I'm just gonna move this graph down because we're gonna make some other graphs here. Because the fact that it's not zero order is not super helpful. We need to know what order is it? Like, is it first? Is it second? So let's go back to our notes. Okay. So I made this graph of concentration versus time. I'm gonna slide back over here. I made this graph and it's not linear. So this reaction is not a zero order reaction. But before I move on to talk about the differences between first and second and how we're going to differentiate between the two of those, I want to talk a little bit more about this graph that we made, okay? When we graphed this, and I told the spreadsheet program to spit out the equation for the line, you know, an equation for a line, you guys, right, is y equals mx plus b. So if I was to try to figure out, like, well, what is the equation of this line really representing? On my y-axis are the concentrations at different points in time. Like, that's what's on my y-axis. My concentration at different points in time is my y. My slope, remember, is equal to negative k. The slope of my line is equal to the negative value of my rate constant. On the x-axis is time. My y-intercept, or b up here, is the initial concentration. Like, that's just what those values are. Like, that is what we graphed. This equation for this line right here, this right here is called the integrated rate law. And this is the integrated rate law for a zero order reaction. Why is it called integrated? Well, integration is just a mathematical tool. You'll learn it in calculus, where you can take an equation and you can integrate it. But we don't need to talk about like how to do integrations. Honestly, I probably don't even remember because I took calculus like 20 years ago. But those of you that have taken calculus know what I'm talking about. And this equation, this integrated rate law, really comes from the integration of this rate law right here, the ones that we learned how to write yesterday. These ones we learned how to write yesterday are called the differential rate laws. Both of these are for zero order reactions. Okay, so like this is the rate law for a zero order reaction. This is the integrated rate law for a zero order reaction. Okay. So now we have to figure out, okay, well, this reaction was not zero order, right? This integrated rate law didn't fit. It was not linear. So what would happen if it was first order or second order? That's where we need to add some notes before we go back to the practice problem. If you have a first order reaction, your differential rate law is rate is equal to k a to the 1, right? Or again, you could just say rate is equal to k times a. Rate is equal to k times a. These are the same thing, okay? These right here are your differential rate laws, if you want to label it. This is your differential. If you integrate this rate law, just like we integrated this rate law, we get a different equation than we got for zero order. The integrated rate law for first order is the natural log of the concentration at some point in time is equal to negative K times T plus the natural log of the initial concentration of A. This right here is your integrated rate law for a first order reaction, right? Take this first order differential rate law and integrate it. So what this is telling me, hey, do you guys like see here, right? Just like this equation was y equals mx plus b, this equation is also written in that same format, y equals mx plus b. In other words, if I were to graph this, but instead of graphing concentration versus time, if I graph the natural log of the concentration versus time, right? If I put this on my y and this on my x, I will get a linear relationship or graph if the reaction is first order. And again, my slope will be equal to negative K, and my intercept will be not the initial concentration, but the natural log of the initial concentration. Okay, so what does all this mean? Well, it means that if I want to figure out, okay, the reaction is not zero order, because when I graphed this, it wasn't linear. Now I need to create a second graph, and I want to see, all right, well, if I graph the natural log of the concentration of A over time, if that graph is linear, then my reaction was first order. So let's go back to the spreadsheet program and let's graph the first order data and see if that is more linear. So I'm going to add a column to my data where I calculate the natural log of the concentration of the NO2. And remember, we can get the spreadsheet program to do the math for us. So you hit equals and you start typing in natural log. What do I want to take the natural log of? Of the concentration. And hit enter. It autofills for me. This is too many decimal places. There we go. More reasonable number of sig figs here. Okay, so now I want to graph this data. So I'm going to select my time. I'm going to use the control button. If you hit control, or if you're on a Mac, I think it might be command, and hold it down, it allows you to select individual columns without selecting that column in the middle. And so now I'm going to insert my scatter plot. And here's my graph. Okay, so you can see my natural log is on my y-axis and my time is on my x-axis. This looks a lot more linear. But remember, the tool that we can use to determine just how linear is this, underneath Customize, go to Series. You're going to add a trend line. Use the equation, show the r-squared value. So here's the equation of my line. Ooh, this r-squared value is a lot better. It's 0.982. So we're getting a lot closer to 1. But we need to confirm by graphing the possibilities for a second order reaction as well. Okay, so I'm going to leave this. I'm going to move this first order graph. Oh my gosh, Google Sheets is so slow. The internet is still not happy. I'm going to put my first order graph over here. Okay, so here's my zero order, definitely not zero order. Here's my first order possibility, maybe. But we need to check this out, and we need to also graph the possible integrated rate law for a second order reaction. So we're going to switch back to our notes. Okay. Same thought process one more time, but for a second order reaction. everybody's like stomping around and grunting in my house. Okay. Second order rate law. The differential rate law, rate is equal to K A squared. Label that if you want to as your differential rate law. If I integrate this, I will get a different integrated rate law. I get 1 over the concentration at some point in time equal to, this time it's a positive slope because we're doing the inverse of a concentration that's decreasing, so really it's going to be increasing. So we're going to get a positive slope here times time plus 1 over the initial concentration. This is the integrated rate law for a second order reaction. You don't need to memorize these. We're going to make a cheat sheet. You're going to have them available. They're on the AP equation sheet. So you don't have to memorize these integrated rate laws. Do you see that y equals mx plus b format for this integrated equation? What this means is, if I were to graph 1 over the concentration at different points in time, times time, or by time, I'm going to get this linear relationship if the reaction is second order, and my slope is going to be equal to K. So let's go back to our spreadsheet and let's graph 1 over the concentration and see if this is more linear. One over. All right, hit equals. That tells the spreadsheet to do the math. 1 divided by, don't divide by the natural log, it's 1 over the actual concentration. So we get the inverse for each of these. Too many decimal places, oops. Okay. And we're gonna graph one more time. Select your time. Select the inverse of your concentration. What the heck happened to all of my options here? There's my chart. Insert a chart. And there's my graph. Now that looks pretty linear as well. So let's add a trend line and see what the R squared value looks like. Again, one last time, it's series, trend line, equation of the line, R squared value. Aha, look, this one is 1. My R squared value is equal to 1. So what that means is that this is my most linear relationship. This graph, the graph of 1 over the concentration. If that's the case, that means that this reaction is second order. If 1 over the concentration is the most linear, this is in fact a second order reaction. And let's try to remember this equation here and write that down as well. So let's switch back to our notes. Okay, so I'm gonna go back to the problem, right? Because this is what we were working with here, okay? So we graphed concentration and time. And then we graphed the natural log of the concentration and time, right? So whatever that information was. And then we graphed 1 over the concentration. And we made those 3 graphs. The R squared value for this graph was terrible. It was like 0.92 or something. The R-squared value for this graph was a little bit better. It was like 0.98. I'm just trying to remember off the top of my head. And the R-squared value for this one was the most linear. That means if 1 over the concentration versus time graph was the most linear, that means that this reaction is second order with respect to the NO2, which in this case was the only reactant, okay? But we can do this for multiple reactants. You just have to look at each reactant individually, one at a time. Okay, so let's summarize everything that we now know about this reaction. If we know that it is second order, we can write the rate law. Rate equals K NO2 squared, right? That's the differential rate law. I'll just slide over here. Okay, so we now know the differential rate law. We also know the value for K. Like, remember yesterday we had to like plug in, we had to pick an experiment and plug in a known initial rate and a known initial concentration, and we could then calculate the K value. We don't have that information all here. We didn't measure rate, we measured concentration change over time. So that's not how we're gonna get K. We're gonna get K just by looking at the slope, right? So remember the equation for this line, I think when we wrote the equation, or when we told the spreadsheet program to spit out this equation, the equation was 0.543x plus 99.8. So that's the equation for my line, y equals mx plus b. So this 0.543 down there, that is my slope, which means that's my rate constant. My units for my rate constant, if it's second order, would be over molarity seconds. Remember, we talked about how to derive these units yesterday. If you forget, go back and look at your notes. Okay, so that's a lot of information. But we also know the integrated rate law. You know, I just wrote it down here. I wrote it in the y equals mx plus b way, but I can also write it in terms of like this particular reactant. Like the y is 1 over the concentration of NO2 at any point in time. That's going to be equal to the rate constant, K, 0.543, times time, plus 1 over the concentration of the NO2 initially, which is my intercept. Okay, so I know the integrated rate law for this reaction as well. And what you're hopefully wondering is like, well, who cares, right? Like, what's the difference between these two rate laws and what are they good for? The differential rate law allows us to predict initial rate based on initial concentration of your reactants, right? So like I can say, all right, well, if I start off with X amount of NO2, how fast is that reaction gonna go? That's what the differential rate law is good for. What the integrated rate law is good for is it allows us to predict what a concentration is going to be at any given point in time, right? So like I knew the concentrations because I measured them in the lab. You know, I know what the concentrations are at these points in time, at 0, 50, 100, 200, 300. But like, what if I want to predict how much there's going to be at like 500 seconds, you know, even later in the reaction? I can use the integrated rate law. this allows us to determine concentration of reactants at any point in time. So let's do that for this reaction. Let's calculate how much NO2 is there going to be at 500 seconds. So it's just plugging and chugging. So how much NO2 is there going to be at 500 seconds? Just plug in your rate constant. Oh my gosh, more people clomping up and down the stairs. Molarity seconds times time, 500 seconds, plus 1 over whatever the initial concentration of the NO2 was, which I think it was 0.01 molar. So now it's just a little bit of algebra. Oh my God, tell me I have a calculator. All right, let's see here. 0.543 times 500. Right. I have this 4-function calculator. I can't even do parentheses. All right, 271.5 plus 1 over 0.01 is 100. Okay, so this is all equal to 371.5. So if I want to solve for the NO2 at 500 seconds, that's going to be the inverse of this. NO2 at 500 seconds is going to be 1 divided by the 375s. Not 375. 371.5. And I get 0.00269 molar, which, let's do a sanity check. If we go back over to our data table, at 500 seconds, 0.00, what did I say it was? 269. Yeah, it makes sense, right? It's continuing to go down, right? From 0.00380 to 0.00269. And you might be wondering, why do I even care about that, right? Why do I care how much there is at 500 seconds? Well, this is really important. Reaction rates are super important, not just in manufacturing, but I'll give you an example that is, really important in terms of just your own life. When you think about reaction rates of medicines, that's super important. Especially if you're thinking about general anesthesia, that's a reaction of a medicine with your body. And so if you're going in to have surgery and, the anesthesia doesn't kick in for an hour, the rate of that reaction takes an hour to, get going and feel the effects. You don't want that surgeon starting surgery until an hour into that reaction. You also want to know how long is that reaction going to last for? At 500 seconds, are you still going to have some of that medicine in your bloodstream, right? 3 hours from now, 4 hours from now, how long is that reaction going to last for? We need to be able to make predictions about how long is that substance going to be in our blood or in our systems. So surgeons know how long they have to complete the surgery. So reaction rates are really, really important, and we use these 2 different rate laws to do 2 different things. Okay. So, in summary, if we want to use this method right here, where we do one experiment to determine the rate law, the steps are as follows, right? You are going to let one experiment run and measure your concentration of your reactant, and you're going to measure time. You are going to graph 3 different graphs. You're going to graph the concentration of your reactant. versus time. You will graph the natural log of your concentration versus time. And you'll graph 1 over your concentration versus time. Whichever one of these graphs is the most linear. Okay, so you are going to run a linear regression. Which is really just a trend line. On your calculators, it's called a linear regression. So you're going to get a trend line. You are going to display the equation and the R squared value. And you are looking for the R squared that is closest to 1, is the most linear. And if it's this reaction, if it's this graph, if it's concentration versus time, your reaction is 0 order. If it's the natural log versus time, your reaction is 1st order. And if it's 1 over your concentration versus time, your reaction is 2nd order. Okay, one last thing that I would like you guys to add to your notes here, this sort of chart that we made up here, where we have information about 0 order, 1st order, and 2nd order, okay? There's one other thing that these integrated rate laws can do for us, and that is they can tell us the half-lives of these reactions. Because remember, half-life is the time that it takes for a reaction to go to half of its initial concentration. So like the half-life for this 0 order reaction would be the time that it takes, T, for your initial concentration, let's say it's 1, to go to a final concentration of 0.5, right? So we can actually like plug in, some imaginary values here and solve for T. And that will be equal to the half-life of that reaction. You guys remember half-lives from nuclear decay reactions. Okay, so let's add these half-life equations to each of our reaction order notes. Okay, so if I were to try to derive what is the half-life, or the time that it takes to go from, 1 molar to 0.5 molar for this 0 order reaction, I would get a half-life equation, T1 half, is equal to the concentration of A initial over 2 times the rate constant. The half-life equation for a 1st order reaction will end up being 0.693 over the rate constant, K. And the half-life for a 2nd order reaction is equal to 1 over K times the initial concentration. Now, what I'd like you guys to notice is that 2nd order half-life depends on initial concentration. Like the half-life is going to change depending on how much stuff you start with. 0 order reactions also depend on the initial concentration. They're going to change depending on how much stuff you start with. But notice for 1st order reactions, 1st order reactions do not depend on the initial concentration. I'm sorry, the half-lives don't depend on the initial concentration. They have constant half-lives. That do not depend of your initial concentration of your reactants. Like nuclear decay, right? Nuclear decay reactions are first order reactions. It doesn't matter how much stuff you start with. The half-life is the same throughout. Half-lives are constant. But that is only true for first order. And that's sort of like a unique way to, it's like another way to identify a first order reaction is by simply looking at whether or not that half-life is constant throughout. But for zero and for second order, that is not the case. Okay, very good. That's it. Again, my apologies. I don't know why I'm apologizing. I feel bad that happened today, but I had nothing to do with the Wi-Fi. So there's a pre-lab to do. There's another video that you guys need to watch to understand the pre-lab a little bit better. And there is a problem set to do that will give you lots of practice at looking at one reaction changing over time, making those graphs, and determining the reaction order. Have a good night.